All right, let's talk about something that sounds a little intimidating at first, but is actually one of the most important ideas in all of chemistry, the mole. We're going to demystify it, because it's kind of like chemistry's own secret super number, the key to understanding the world of atoms. Let's dive in.
So picture this. You're a chemist, right? And you've got this huge problem. Atoms and molecules are so small you can't see them, and there are billions upon billions of them in the tiniest speck. So how in the world do you write a recipe when your ingredients are individual atoms? Well, that's exactly the problem the mole was created to solve.
So here's our game plan. We'll start with a simple idea I'm calling the chemist's dozen. Then we'll get into what a mole really is. After that, we'll see how to get from moles to grams, something you can actually weigh. We'll look at moles in a solution, and then finally we'll put it all together and solve a problem.
Okay, before we get into the nitty-gritty, let's start with something you already do every single day without even thinking about it: counting things in groups.
When you go to the store, you don't ask for 12 eggs, right? You ask for a dozen. You don't ask for 500 sheets of paper, you ask for a ream. A mole is exactly the same idea. It's just a convenient name for a group of specific number. It's just that for chemists, that number has to be, well, a lot bigger. It's the chemist's dozen.
Okay, so we've got the basic idea down. It's just a big counting number. But what is a mole really? And where did this so-called magic number even come from?
Well, here's the official textbook definition. A mole is the number of atoms you'd find in exactly 12 grams of a specific type of carbon, carbon-12. What that really means is, it's not just some number pulled out of thin air. It's tied to something real, something scientists can actually measure and all agree on, which is absolutely crucial.
And we have to give a shout out to the guy whose work made this all possible, the Italian scientist Amedeo Avogadro. Now, he didn't figure out the number himself, but his work laid all the essential groundwork, so the number is named in his honor.
So what does this number actually look like? Brace yourself, it's that. That is a ridiculously, mind-bogglingly huge number. But it has to be, right? Because we're counting things that are unimaginably small. Just look at all those zeros.
Yeah, nobody's got time to write all the zeros out. So instead, chemists use scientific notation. It's 6.022 times 10 to the 23rd. This is what's known as Avogadro's constant, and it's the number of particles, atoms, molecules, whatever, that are packed into a single mole. All right, so a mole is a counting number. Cool. But how does that actually help us in a lab? I mean, you can't see atoms to count them. This is where it gets really clever. This is how we build a bridge from the invisible world of atoms to the very real world of scales and grams.
And here's the absolute best part, the secret that makes it all work. It's so simple, it's brilliant. To find out how much one mole of any element weighs, all you have to do is find its atomic mass on the periodic table and just call it grams.
Seriously, the periodic table is your best friend here. It's basically a cheat sheet. You see that number under each element, the atomic weight? Well, for carbon, it's about 12.01. That means 1 mole of carbon atoms weighs, you guessed it, 12.01 grams. 1 mole of hydrogen atoms, about 1.008 grams. It's that direct.
Okay, that's easy enough for a single element, but what about a compound, something like ethanol? It's just like following a recipe. The formula C2H6O is our list of ingredients. It tells us we need 2 moles of carbon, 6 moles of hydrogen, and 1 mole of oxygen. We just add up the mass of all those parts, and boom! 1 mole of ethanol weighs 46.08 grams.
Okay, let's switch gears a little. In the real world, chemists aren't always just weighing out pure solids. A lot of the time, they're mixing things into solutions. So how does the mole help us there?
And to do that, they use a concept called molarity. You'll see it as a big capital M. And all it is a way to measure how concentrated a solution is. Basically, it's the number of moles of your stuff divided by 1 liter of the total solution. The higher the molarity, the more stuff is dissolved in there.
So if you were in a lab, how would you actually make one of these solutions? Well, to make a 1 molar solution, you'd go to the scale and weigh out exactly 1 mole of your substance. Then you'd put it in a special flask and add just enough water to get the total volume up to exactly 1 liter. That's it.
And the math behind it? Super straightforward. Molarity equals the moles of what you dissolved, the solute, divided by the total liters of solution. Which is great because it means if you know any 2 of these things, you can always figure out the third one.
And hey, if you're like me and sometimes you blank on how to rearrange formulas, this little triangle is a lifesaver. You just cover up the thing you're trying to find. Want moles? Cover it up and you see molarity times liters. Need the volume? Cover that up and it's moles divided by molarity. So handy.
Okay, theory time is over. Let's put this all together and see how it works in a real problem. Let's actually put the mole to work. So here's the challenge. We've got half a liter of solution, and we know there are 6 grams of sodium hydroxide, or NaOH, dissolved in it. The question is, what's the molarity?
So what's our game plan? It's a pretty simple two-step process. First, the molarity formula needs moles, but we were given grams. So step 1 has to be converting those grams into moles. Then, once we have that, step 2 is easy. Just plug our numbers into the molarity formula.
All right, step 1, that conversion. We just need the molar mass of NaOH, which, if you add it up from the periodic table, is 40 grams per mole. So we take our 6 grams and divide by 40 grams per mole. The grams cancel out, and that leaves us with 0.150 moles. Perfect. And now, the easy part. Step 2. We take our molarity formula, M equals moles per liter. We plug in the 0.150 moles we just calculated and divide by the half a liter we were given, which gives us our final answer, 0.300 moles per liter, or as a chemist would say, a 0.300 molar solution. Boom! Done!
So there you have it, the mole. It starts out seeming like just a crazy big number, but it's actually this incredibly elegant bridge that connects the invisible world of atoms to the world we can actually measure in the lab. It makes the invisible visible and the uncountable countable. So the only question left is, what will you go out and measure?